This video covers moving charges. So we said in our last video that there's a force of magnetism on moving charges. So if a moving charge moves through an external magnetic field, meaning the field due to another magnet, then the two magnets will interact. Now there will be an equal but opposite force on the charge and the external magnet. However, the charge is very small and the external magnet is very large. As a result, we will see the charge affected by the force when the same force creates negligible effects on the external magnet. What that means is that the magnet is so large in comparison that we're not going to be able to see the effects. So, the force of magnetism on a charge moving in a magnetic field is described by this equation, where Q is a charge in units of coulombs. V is velocity of the charge in meters per second, and magnetic field is represented by B, and again we have units of Tesla. This is one of the most important parts, that this angle is referring to the angle between the vectors V and B, between the velocity and the magnetic field. So if we look at the previous equation, that means that we have different situations where we can actually not have a force at all, even if we have a charge moving. So I'm going to write the equation down here. In the first example, we don't have an object that's moving, so we have no magnetic force acting on it. In the second example, our object is moving, but if you notice, the velocity is in this direction, the magnetic field's in this direction, so my angle between them is actually 0. So if my angle is 0, then my sine of theta is also 0. So my force is also 0. Here, my velocity is to the left, my magnetic field is to the right, so my angle is 180 degrees. So, sine of 180 is also 0. So then we have another 0 force. Now, here where our force is, or our charge is moving perpendicular to my field, then my angle is 90, so my force is actually maximum at this point. Now this is going to create circular motion, but we're going to see that in just a few minutes. Here we have an angle that's created between our magnetic field and our velocity vector, so we have to use the full equation. And again, this is going to create a spiral effect. So again, the biggest thing to take out of this is that force only occurs if there is a component of velocity that is perpendicular to the magnetic field. If that's not true, then we have no force produced by the magnetic field. Now again, these pictures look very similar to what we saw in electricity or electrostatics. So here, I want you to take some time to notice the differences between these two. On the top, we have our magnetic field, and at the bottom, we have an electric field. So even though we have a velocity of 0, we had 0 force. This one did not depend. Our electric force, did not depend on any angle. So even though we weren't moving in this situation, we still had a force. So make sure that you can remember the differences between these two. Now we said that it was going to cause circular motion. So what that means is if my force is perpendicular to my tangential speed, or my speed in this situation, then my magnetic force is going to be a centripetal force, meaning that we can set these equations equal to each other. Also remember that centripetal acceleration is v squared over r. So we have another version of that equation. So just like before, anything that we had to do with circular motion, we can also apply period is equal to 1 over frequency, or that velocity is equal to 2 pi r over period. Again, these are old functions. So here we have a proton moving at 5 times 10 to the 4th power in a 10 Tesla magnetic field at an angle perpendicular to the electric field. So we're asked to solve for the force. The force is equal to Q, V, B, sine of 90, which is just 1, so you can leave that out if you wanted to. The charge is 1.6 times 10 to the negative 19 because it is a proton. The speed is 5 times 10 to the 4th, and the magnetic field is 10. So that gave us a value of 8 times 10 to the negative 14 newtons, because it's a force. Now we're also asked to solve for the radius of the proton from the resulting motion. Again, we said that this is going to cause circular motion. So this force, which is 8 times 10 to the negative 14, is equal to mv squared over r, our centripetal acceleration times our mass. And we wanted to solve for r. So that is mv squared over 8 times 10 to the negative 14. Here we're using the mass of a proton, which is 1.67 times 10 to the negative 27, I'm sorry. And 5 times 10 to the 4th, which was our speed. And 8 times 10 to the negative 14, which was our force. Gave us a radius of 5.2 times 10 to the negative 5 meters. Again, we should get a very, very tiny radius here because those circular motions are going to happen very quick, so those radius are not going to, or those circular motions are not going to be very large. In this example, we have a proton moving at 2 times 10 to the 4th meters per second that enters a magnetic field, causing it to follow a circular path of radius 1 times 10 to the negative 3. And we're asked to determine the strength of the magnetic field. Again, these problems are really simple, so I went ahead and just included the calculations here. Again, your magnetic force is equal to your centripetal force. So QVB is equal to mv squared over r. And we can rearrange this equation to solve for our magnetic field, B. Here we went ahead and plugged in all of our information. Again, m is the mass of a proton. V was our speed. Q was the charge of a proton. And r was the radius of that. And when you plug in all of your information, you get 0.21 Tesla. Another really easy plug-in chunk. You have your information and you're asked to solve for the force. So again, just putting in your charge, your speed, and your magnitude of your magnetic field. And then do not forget that the angle is the angle between your velocity and your magnetic field. So then you get a force of 9.62 times 10 to the negative 14. Now this is an extension of the right-hand rule that we saw in our last video. So remember that for a right hand, you're going to need to use, for a positive charge, you're going to need to use your right hand, whereas for a negative charge, you're going to need to use your left hand. So remember to follow these particular directions, that your fingers, your extended fingers, are going to go in the direction of your magnetic field. Your thumb is going to go in the direction of your velocity, and your palm is going to go in the direction of your force, so that they all create perpendicular angles, or all create 90-degree angles. So in this first one, we have a magnetic field that goes to the left. We have a velocity that goes into the page. Again, we're seeing this X, so it's telling us it's going in. So our thumb will be going in, our fingers will be going to the left. That means our palm goes up. We have a force going upwards in the positive Y direction. Here we have an electron, so that means you need to switch over to your left hand. So you have a velocity that goes into the page, so your thumb goes into the page. Your fingers, well, here we're looking at our force, so this is our palm, which means that we're going downwards. So our extended fingers, which represent your magnetic field, is going to go to the left in the negative X direction. here we have a few more examples that you should try doing on your own. This first one, you're given that it's a proton. Your fingers go in the direction of the magnetic field. Your force goes down, so your velocity will go into the page. Again, what's in red are the answers to these little problems, so make sure you're trying these for yourself. We're just going to go through them so you can see what they look like. Go ahead and pause the video if you need some time to think about these. Okay, so now we're going to look at drawing the motion of charges in magnetic fields. Again, we said we're going to have circular motion here. What we see in these X's are the magnetic field lines. It's telling us that the magnetic field is going into the page. So again, our fingers are going into that direction. Our thumb is going to the right, but make sure that you notice here that this is an electron. This is a negative charge, so you should be using your left hand here. So that means that our force is going to be in the negative y direction. So if my force pushes my charge to essentially accelerate in that direction, we're going to start having this curve in the clockwise direction. Again, this looks identical to circular motion. We have a force that goes towards the center of the circle. We have a velocity that is tangent to the circle. And that, again, creates that circular motion. So again, we'll have a more example so you can test those directions for yourself. So again, make sure that you're pausing the video and trying these out so that you can tell whether or not you're doing these correctly. Again, the X's tell you that you're going into the page. The dots tell you that the magnetic field is coming out of the page. Also, make sure that you're careful looking at whether these are negative or positive charges. So again, here we have a proton moving in the positive x direction. It enters a 15 Tesla magnetic field that is directed in the negative z direction, again going into the page. It follows a circular path with a radius of 8 centimeters. So again, make sure that you are drawing the direction of the force so that you can also draw the direction of your circular motion. And then we're asked to solve for the speed of the proton and the direction of the path, which we've just finished. Again, we're putting it all together. We solved for our speed. We're asked to solve for our speed, and we have enough information to calculate our force. So we have mv squared over r is equal to qvb. At this point, we can actually cancel out one of our velocities. And so our speed will be equal to q times b times r over m. Again, most of this information is constants. 1.6 times 10 to the negative 19 for a charge. Our magnetic field strength, which was 15, is given to us. Our radius, which is 8 centimeters or 0.08 meters, is also given to us. And then the mass is another constant. We have 1.67 times 10 to the negative 27 because it is a proton. If you put in all of your values, you should get 1.15 times 10 to the 8 meters per second. Now let's say we have a combination of field problems. Now, on the left-hand side is what we've seen in electricity before, and on the right-hand side is our magnetic field. So again, we're going to use the battery to tell us the charges on the plates. Long side tells us positive, short side tells us negative. It's going to accelerate through those plates, and we're going to use our QV 1/2 v squared equations. So again, we can solve for the speed as it goes through those plates, and then figure out the direction and how it's going to be moving once it enters a magnetic field. And then you can use all the particular equations that we need depending on the situation. So again, use this information to help you figure out the direction and what charge you're looking at and how it's going to be acting. Go ahead and pause the video, try all of them out on your own. You can just go ahead and make some sketches, and then you'll see the answers in just a moment. A couple of more examples. Make sure you're pausing the video, trying them out. And then finally, let's go ahead and put it all together. Here we have plates in the diagram that have an electric field of 20 Newton per coulomb, and they are separated by 10 centimeters. The magnetic field has a strength of 5 teslas. We're asked to determine the radius of the particle's path. Okay, as always, first start off by labeling your plates, figuring out what charge we have. We're going to use some information to calculate the speed it gets or has by the time it exits these plates. And then we can use our right-hand rule to determine the force acting on it. And then the direction of its movement. Again, here you're asked to solve for the radius of the particle's path, but you're not given the initial speed, which is one of the initial conditions. So that means you need to solve for that speed. What we're going to do is we're going to use information from electrostatics, which means that we just figured out that this is a proton, that these two plates have a strength of 20 Newton coulombs, so that's our electric field, and that the distance in between these two plates is 10 centimeters or 0.1 meters. So with this information, we can actually solve for V, our potential. So that's 20 times 0.1, which just gives us 2 volts as our potential difference across these two plates. Now, we've said before that we can use our potential difference and the fact that we know it's a proton that moves to solve for the speed once it exits these plates. So again, Q is the charge, in this case a proton, and I want to get V by itself. Again, you should remember all of this. Again, the charge is a proton, so I know it's going to be 1.6 times 10 to the negative 19. The potential we just solved for was 2. And then our mass is going to be 1.67 times 10 to the negative 27. Once you put all of that information in, you should get a final speed of 1.96 times 10 to the 4th meters per second. Now again, this is the speed as it leaves this point right here. So if we wanted to use that information to help us solve for the radius, we can do what we did in previous examples. mv squared over r equals qvb. Our velocities can actually help us cancel and clean this up. And we get r is equal to mv over qb. Go ahead and plug in all of your numbers. You should get a value of 4.09 times 10 to the negative 5 meters. Now, again, we were also asked to solve for the direction of the force, which we said was downward, because our speed was in this direction, our velocity. So that's the direction of our thumb. We said that our magnetic field was coming out of the page. So we have our thumb that goes up. Actually, our thumb goes to the right and our fingers come up, which means that our palm is going to go downward. And then we're asked to determine the direction of the charge as it moves in the magnetic field. Again, we said that follows that circular path. So again, we just used all of that information to help us solve for the strength of the magnetic field. Now we can use that information to help us solve for the magnitude of the force. Again, F is equal to QVB. Now at this point, we don't even need the wire anymore because we've already determined that an electron is passing at this point, so 1.6 times 10 to the negative 19, that it's moving at 6 times 10 to the 5th meters per second. And then we just solve for the strength of the field, which is 3 times 10 to the negative 5th Tesla. It's okay, it's a small number because, again, this is outside of our wire, so that's not unusual. Again, our force, you should get a number very close to 2.88 times 10 to the negative 18 power. And then we're asked to determine the direction of the force on that electron. Again, we said if our magnetic field comes out, our velocity goes to the right, then our force must be upward in the positive y direction.